Thank you, Marco. All right, so yeah, I'd like to start off by saying that this reanalysis of the boss data will be based on a bunch of different codes and software and theory that was developed by a big group of people. So all these things are publicly available. So here I'm listing some of the tools that will be needed for today's tutorial. So really, okay, maybe I should say first that um, there is a Google Colab. So this slide contains the links to all these different parts of the analysis that I'm going to show, and this Google Colab basically is one of them. And then there will be other links and that you will see explicitly directly to some of these important software codes that will be needed. But in general, I will make this slide available, and then you can click on these things on the Google Colab notebook that kind of shows you the workflow, and then also it has all the links to the GitHub, or mostly GitHub codes that contain the original code. So the idea of this, as Marcus said, to combine all these different ingredients into one analysis that will hopefully discover some new physics. And this, well, in the actual data, obviously, right? So in that case, there will be several steps. The first step will be to have the code that contains all the necessary new physics, and as Julian presented very nicely, we have the class code that contains already a lot of BSM models, and also it's, class code is relatively easy to modify. So if you have a new model of your own, you can always include this. Then if you want to analyze the Galaxy clustering data, you would have to use some of these EFT tools that are also coded in, well, at the moment in different codes that are either external or based on extensions of class. So one of such code that we did with collaborators, including Marco, is called class PT, which, well, is a version of class. But unfortunately, by writing this version, I violated the main class commandment. So I used an external library. So I created the schism in class. So that's why it's not an official class version. Well, you will see if you open also this Google Colab notebook, it starts by downloading the BLAS library that takes, and installing it, that takes about 15 minutes, which is very annoying, but it's also 15 minutes, you can take a coffee and come back and it will be installed and you don't have to worry about this again. Okay, right. Then for this workflow also we'll have to obviously work with the data and to build the likelihoods, we need to extract this data from the, let's say, raw data of the surveys. And for the Galaxy surveys, such as BOSS, this, well, there are several steps. The raw data includes the spectra. And then, from the spectra, you can go to the Galaxy catalogs. So I'm going to cover the part where you go from the catalogs already to the estimation of the power spectrum. There are very efficient tools that can do that, such as NBodyKit and also PolyBean 3D code. And then once you have these measurements, you can build a likelihood using the usual principles of building likelihoods in data analysis. And once you have this likelihood, you can use your favorite MCMC sampler to sample the parameters of your model. So in my case, I'm going to cover this Monty Python MCMC sampler that was developed by Benjamin Odren and Julien Lesgourc and collaborators. And once you have all these things working together, then you can analyze your models and you can think about adding external data sets. And this is just to say that my today's work will be based primarily on BOSS, but as you know, BOSS is not the most constraining and not the most recent Galaxy survey. So we also have some eBOSS data. eBOSS, for instance, contain the Lyman alpha forest correlations that I'm not going to cover, that in principle also you can find online. This data is publicly available and its EFT-based full shape likelihood will be publicly released soon. And also right now, we're working with Oliver Filkux and Atle Chudaikin on releasing the public likelihoods for the DAISY that are based on the EFT-based full shape analysis. So please stay tuned. But for this, for the purpose of this tutorial, I'm going to focus specifically on the BOSS data where things are well established. And then obviously you can apply kind of the same logic to other data sets. All right. To start off, let me say again a few words about this class PT. So class PT is an extension of class that contains a huge number of different nonlinear calculations. So the idea is to really make a universal EFT library. Already now we have all the correlators for the power spectra at one loop for matter, galaxies, SIMB lensing, involving all necessary cross correlations. We also have the loops due to primordial non-Gaussianity that are important if you want to extract constraints on the amplitudes of primordial non-Gaussianity from the data. And then there are a bunch of updates coming up soon, such as the Lyman alpha one loop power spectrum that includes additional operators due to the Lyman alpha breaking some of the symmetries and kind of concentrating around the line of sight. Then also for specialists, this new update will have the field level transfer functions for simulation-based priors based on the work that Marco developed. And this is something that will allow you to get really very informative priors that play a significant role in constraining cosmological parameters. And other things will include the one loop bispectrum. And hopefully the idea is to publish this all updates as a new module that will be totally external. So this way the schism will end and it will be only one class. Okay, so keep an eye on these things and stay tuned. Now, in terms of the BOS data, what we're going to look at today will be the full combination of the BOS datasets that at the moment includes the measurements of the galaxy power spectrum multipoles that you can see here, the monopole, the quadrupole, and the hexadecapole, from 4 different chunks of the BOS data. So BOS has coverage for the north part, North Galactic Cap and South Galactic Cap, and also it has a redshift coverage going roughly from redshift 0.2 to redshift 0.8, and this galaxy distribution then is split into 2 bins, more or less, that are called Z1, Z2, or low Z CMAS. You can do different selections. So there will be basically four copies of this data set. Also, it includes the bispectrum, including the bispectrum multipoles, and also I'm going to talk about the cross correlation with the SIMB lensing. You also have measurements. SIMB lensing you can get from Planck or from ACT. Again, this data set is public. One caveat, maybe I should say, is that all this data set with all these extra ingredients and calculations included is in a little bit of a tension with Planck in terms of this sigma 8 value. So it seems that the tension now is about 4 sigma. And obviously, you've seen the DAISY results on the full shape, and then they don't find any tension. So there is obviously kind of a discrepancy between BOS and DAISY. So, okay, this is something to keep in mind. It's unclear what it is, but I'm sure that this is a systematics because BOS and DAISY basically have coverage for similar galaxy types. So if you compare the power spectra for the same galaxy selections, you will see, same redshift ranges, you'll see that the power spectra are slightly different. So obviously some systematic is going on. So this is something important to keep in mind. All right, now the workflow that I'm going to go through today will be first download the catalogs, then estimate your statistics of interest, power spectra, bispectra, be your covariance matrices, etc. Build a likelihood with the likelihoods run MCMC code, and then hopefully discover your favorite model and then collect the Nobel Prize. Okay? So let's go through it. The first part is the catalogs. Okay, most of the results of the galaxy, data collected by galaxy surveys such as BOS and also DAISY, DAISY year 1. So all these things are publicly available. If you know what you're doing, you can go to the level of the raw spectra and then follow the kind of algorithm outlined here on the official BOS website that tells you how to organize, selection and work with the weights and stuff like that to construct high fidelity galaxy catalogs. Now, if you're, less familiar with all these astronomical technicalities, you can just go to the BOS website and download already the catalog that are formed by selecting the most optimal option. And this catalog that you can combine into, let's say, CMAS and low Z, or maybe Z1, Z2, depending on what kind of redshift cuff you want to do. But in principle, you can already work with these catalogs on the right. Now, the estimation of the power spectrum and covariances is also well established step. And there are several tools, great tools available online. So one of them, which is kind of the standard one, is to use the n-body kit. So n-body kit is the code that will compute the usual windowed power spectrum that Elizabeth introduced here. So the window power spectrum using the FKP estimator. And this calculation is extremely fast. Like really, you can do it on your laptop in a couple of minutes. Now, there is an alternative way to estimate these things based on the window-free estimator developed by Oliver Philcox. And Oliver on his GitHub page has an extensive set of tutorials that will show you exactly how to compute the power spectrum using the window-free method, using the usual n-body kit, and the comparison between the two, and also how to estimate the covariance matrix from simulations and the bispectrum and these kind of things. So this could be a topic of its own tutorial, how to estimate these things properly and efficiently. But let's just say that at the moment, for both, so we have the measurements, we also have the mock catalogs, so of the simulations that are designed to reproduce the galaxy clustering properties, the redshifts and the footprint of the data. So there are about 2,000 of such simulations. So then this means that you can kind of brute force and compute the covariance matrix just by using the empirical estimator that Elizabeth introduced. And this is going to be the major, kind of the main choice of the covariance matrices that we're going to use, although I'm going to comment a little bit on the other techniques to estimate the covariance that Elizabeth mentioned. All right, so maybe, okay, I was about to, okay, maybe I'll show this later. I wanted to walk you through some of these notebooks by Oliver. You will see a lot of nice pictures there, with the footprint and everything. So I really recommend that you guys check this out. It's going to be a lot of fun. But let's move on now in the interest of time to the next step, which is building a likelihood. So if you want to build the likelihood, you have to understand what code are you going to use for that, for the MCMC estimation. So the code that is widely used for these things is Monty Python, that was designed by Julien Lisgourg and collaborators on the left. So you can download this code from the GitHub. And I should also say that Monty Python has an extensive library of likelihoods for other experiments. So you have the CMB, you have supernova, you have all possible kinds of things you could use. So really, Monty Python is an amazing tool. So what we did with BOSS, basically, once we had the measurements, I wrote the likelihood that parallels the logic and the structure of typical Monty Python likelihood. And basically, the typical likelihood will, the logic of Monty Python is that there will be separate files that control different things about your likelihood. There will be the code that just evaluates the likelihood. Then there will be a separate kind of folder that contains all the data in like TXT format, basically, like just the rows and columns with numbers. And then there'll be a parameter file that will specify which parameters you are going to vary and the priors you are going to use. And then it's just a Python code that combines all these things together and runs the usual MCMC. And there are many, I should also say, there are many advanced algorithms that are already implemented in Monty Python. So it's a really nice library. Okay, so once you downloaded these things, we already have the full shape likelihoods that are basically just built in a structure parallel to that kind of matches the logic of Monty Python. So okay, now you have the likelihood. And the most important part here will be this parameter file, which is just basically a text file that contains all the cosmological parameters and other information. So typically here, maybe you can, I'm not sure if you can see it well, maybe I can switch. So let me do the following. Let me switch to my browser and walk you through this parameter file so you can see these things a little better. Okay. So this is the collab file that I prepared. And here, so basically in the data experiment, you specify the experiments that you want to use. So here it will only use the EFT full shape likelihood, but you can add CMB likelihoods, supernova likelihoods, etc., just separated by comma. And then you have to specify the oversampling of nuisance parameters. So when you sample nuisance parameters, you don't need to sample cosmology again because the cosmology is fixed, and typically nuisance parameters you need to sample much more often, but also it's computationally cheap to sample those, again, because you don't need to recompute the cosmological module that takes most of the time. So in that case, it makes sense to sample nuisance parameters more often. And in this field, data oversampling, basically you have to specify how often would you vary nuisance parameters with respect to the cosmological parameters. And in principle, you should define this for every single likelihood, you should define this number. And here in this particular case, I'm sampling the nuisance parameters 3 times as more often than the cosmological parameters. Then there are some fields that specify the parameters that you want to test. So this is the param file from the official likelihood from Oliver's GitHub, and this particular parameter file is designed to sample parameters of the cosmological collider model. So in that case, the cosmological parameters are kept fixed, but we can easily uncomment them. And then you can see that here we just can specify usual parameters of lambda CDM, omega baryons, omega CDM, little h, some kind of parameter that controls the amplitude of primordial fluctuations. So Planck likes to use this logarithm of 10 to minus 10 times the initial amplitude of scalar fluctuations, but you can also scan over other combinations, like you can scan over AS. And then the tilt, and if you want, we can also here sample neutrino masses, depending on whether you want to sample like a single neutrino mass. You know, so as you know, what Planck assumes, and typically Sim-Big experiments assume, they assume that there is a single massive species of neutrino, and typically they fix its mass. But here in this case, you can kind of scan over its mass. And if you want to be more accurate, you would want to allow, you know, for neutrinos to all have masses, and in that case, you can scan their total mass and total. But in general, the idea is that you just specify the parameters that you want to sample. You specify the prior bounds. You specify the initial standard deviation of the parameter that is used to build the likelihood. To build the covariance matrix for the MCMC extraction. And then you also specify the scale. So for instance, for the baryons, since omega baryons, which is the physical density of baryons, is typically very small, it's like 0.022, it makes sense to scan over omega baryons divided by 10 to minus 2 or multiply by 100. So that's why you put the scale 0.01. And in this case, the values of omega baryons that you kind of scan over are going to be in you know, of the order of few. Okay, so you specify all these things. Some parameters that you fix are specified here. In large-scale structure analysis, typically these parameters are the BBN parameters and the parameters associated with the reionization. So Z reionization, well, I guess here, Z reionization or tau reionization. So those are the parameters that you need to fix. And the BBN large-scale structure is not very sensitive to the BBN, so you can just fix Y helium to 0.2454, which is like a best fit from Planck. And this is totally fine. I mean, you can scan over this parameter, but the large-scale structure doesn't have constraining power on it. Okay. And then some other parameters. So you can specify, well, in this particular case, that you want the nonlinear corrections to the galaxy power spectrum be computed. So in class PT, you can specify whether you want high precision or low precision or normal precision. So right now it's at normal, which is using 256 frequencies in the FFT transform that Julien was discussing during his tutorial. And then you say, yes, you want to implement IR summation, you want to have stuff for bias tracers, you want to have Redshift space distortion corrections, something that is relevant for neutrinos, you would want all these things to be evaluated for the fluid that consists only of cold dark matter and baryons. So in the case of neutrino, it's a subtle effect that simulations suggest that neutrinos, they mostly, sorry, in the case of neutrinos, the galaxies, they mostly trace only the cold dark matter and baryons, so they're not sensitive to, well, their sensitivity to neutrinos is suppressed. Like the normally when I was writing down the bias expansion, I would say that galaxies trace all of the matter field, that would include the neutrinos, but somehow simulations suggest otherwise. And in principle, a more robust way would be to include an additional kind of biases, additional bias for CDM and dark matter, an additional galaxy bias for the neutrino field. But it's a small effect, so for the current service, it doesn't matter. So that's why the standard thing you can do is to just evaluate all the bias tracers with respect to the CDM plus baryon fluid. And finally, here also you specify that you would like the Alcock-Paczynski distortions to be implemented and specify the fiducial parameter, fiducial cosmological parameter for it. So the idea of the Alcock-Paczynski distortions is, well, basically that you would want to go from the, from the sky plane and redshift to the usual Cartesian coordinates, but for that, you need to assume some cosmological model, and typically the way how it's done, some fiducial cosmological model is chosen that matches, let's say, Planck lambda CDM best fit, and then you reconstruct the three-dimensional power spectrum using this fiducial cosmological model, and then if there is some mismatch between that, this mismatch will produce observable distortions of the galaxy power spectrum on top of Regis space distortions. And this is an effect that you can then use to constrain your cosmological parameters. So when you do this conversion, typically you assume some fiducial cosmology, and if you measure the power spectrum in units megaparsec over H, the only cosmological parameter that matters in a lambda CDM model will be omega matter. So here you specify the fiducial omega matter parameter. So I'd like to say that this parameter is always kept fixed, is designed by the survey. So when, for instance, when you go to the BOSS website and download the BOSS catalogs, they already use this value 0.31. So it doesn't make any sense for you to change it because that's the value that was used to produce the catalogs. Okay, you don't have to scan off this parameter. So this is using slightly different values. So that's why it's nice to have this as an external parameter you can change depending on what survey data you're analyzing. All right, so when all these things are specified, you can run your MCMC chains. And well, now go back to my slides. So once these things are prepared, now you can run your MCMC chains. You can see, you can find the examples in the Google Colab, but basically the idea is, yeah, there are simple, very simple commands that will run your chain, and you'll specify how many steps do you want to be computed, and then Monty Python is parallelized, so you can specify how many cores do you want to use, and then for each core you'll be computing, a separate MCMC chain that will have its own walker. So in this case, I'm running a small chain with 40 parameters, with 40 steps. So it produces, these 40 steps, and it prints out the steps that are accepted. And here it will show you the initial covariance matrix. Or maybe, yeah, something that I forgot to mention is that also your likelihood will depend on all these EFT parameters that are nuisance parameters. So you can scan them more often. So you should absolutely specify that you need to scan nuisance parameters like 3 or 4 times more often than the cosmological parameters because you have a lot of them. And here in this likelihood, you can see that you have a few cosmological parameters. So 5 cosmological parameters of lambda CDM. So the tau ionization is fixed to a value because large structure cosmology is not sensitive to it. And then the rest will be a chain of nuisance parameters. And each galaxy sample should have its own set of nuisance parameters. And the only nuisance parameters that enter the likelihood, let's say quadratically or cubically, or in some other complicated way are B1, B2, and BG2. And all the other parameters to enter your theory model linearly, like all the counter terms that we'll discuss today. And if you have a parameter that appears in the likelihood linearly, it means that the likelihood is quadratic. Sorry, that appears in the theory model linearly. It means that the likelihood will be quadratic because the likelihood is model minus data squared divided by the error. So it means likelihood is quadratic, and you can marginalize over this parameter analytically because the likelihood of this, with respect to this parameter is just Gaussian. So this is a standard trick that is being used very, very widely. And Julien, in his talk, was showing some of the results when you do the full sampling of all parameters, analytic marginalization, you always get the exact same answer just because, it's math. Okay. So all these other parameters are not specified. They're sampled, kind of not sampled explicitly, but then you can always recover the posteriors for them using some simple linear algebra. Okay. So now, so you started with this MCMC chain, and you run it for some amount of time, and then you will end up, you will generate, chains that are much longer than that you can use to analyze your data. So here, okay. So here I have another notebook that represents some other steps. At some point, it kind of turns on and starts discussing this results of the MCMC chains. So maybe what I will do here, I will first go through some MCMC chains, and then I will discuss some other variations of the analysis that will include, the covariance matrices and stuff like that. All right. So you upload the chain, the MCMC chains, just some TXT file, and then you can plot the posteriors for cosmological parameters. So in this particular case, what I'm doing is that, well, I was sampling all the cosmological parameters, well, assuming only BBN prior on omega baryons. I was not assuming any prior on the tilt. So I get the following posterior distribution for the power spectrum tilt. And you can see that, I mean, it's nice that it can be constrained in principle, but the posterior is extremely wide and goes to very small values up to 0.75. And if NS were 0.75, you would say that you would rule out inflation. So obviously this is a little bit of an extreme value. So you would want to use a prior. Do you have a question? Yeah. Yeah. So -1 right now means no smoothing, right? Sometimes if you have maybe, well, you could kind of even see that in some of this constraint. Well, you see some kind of strange distribution after you apply the prior. Yeah, this smoothing is chosen in the following way. You make a plot, and if it looks bad, you apply the smoothing. Okay, that's it. Yeah, you erase information, yeah. But I mean, ideally, you would want to sample your parameters dense enough. You want to create long enough MCMC chains, so the smoothing should not be needed, right? So, or in other words, like the default smoothing will work, which is kind of, small one for this particular case. But sometimes you can have a complicated run. Sometimes your, walker gets stuck, and then there are some regions that are not sampled as good, and then you can apply the smoothing. Sometimes you can have a lot of samples, and everything is very nice, but for some reasons the plot don't look good, and then you apply the smoothing too. So, right, but typically, typically you run long enough chains, so you don't need to use the smoothing. Okay. All right. So here in this plot, then, okay, it makes sense to use. You can see that NS cannot be well constrained. You apply the prior from Planck. Now you can see that after applying the prior, basically this parameter is nailed by the prior, and then you can see that also it will kill some of the degeneracy directions. Like for instance, the tilt is degenerate with capital omega matter. So you can reduce the width of the posterior quite significantly this way by killing the degeneracy. So it seems to be, also a good idea for this reason to use external informative priors. Well, anyway, now you can test, well, you can check what are the different, statistical information, things that you can get in your MCMC chains. You can output the marginalized means and 68% confidence level intervals, 95% confidence level intervals, etc. You can also test the best fit values and the values of the likelihood. So in this particular case, now you can check, what are the best fit parameters for omega baryons and other, cosmological parameters, and also some EFT parameters. Well, in particular, you can see that linear bias is always around 2 for all these samples, which makes sense because, this is the value that you expect from this particular type of galaxies, early luminous galaxies of BOSS. So everything seems to be making sense. So now what you can do is you can try to take a look at the best fitting curve. And so as I mentioned before, currently all the likelihoods that are available, they use the analytic marginalization over nuisance parameters. So if you just plot the best fit theory curve evaluated for these parameters only, you're going to get a disastrous result because secretly you also have a bunch of other parameters that you need to optimize that have been optimized by means of analytic marginalization. So if you want to build a nice best fit, you need to reconstruct the other nuisance parameters, which is very easy, again, given that your likelihood has a simple dependence on them. So just a linear algebra problem, how to get them. And basically here below, so I attach a little code that reconstructs this extra nuisance parameters. So we take all the cosmological parameters from the chain. We take the B1, B2, and BG2 parameters from the chain as well. Then we compute the matter power spectrum and all the nonlinear corrections for this particular best fit cosmology. And then this little code basically just reconstructs the best fit parameters that have been analytically marginalized over. And it also reconstructs the covariance between them. And we can take a look, for instance, at the diagonal elements of the inverted covariance, which will tell you basically the approximate estimate for the marginalized limits on the analytically marginalized parameters. And on net of this, you can see here some information. So you can see the best fit values of these extra parameters. So the extra parameters that appear here, CS0, CS2, and CS4, basically are the 3 k-squared type counter terms. So CN0 is the, well, basically conceptually like the higher derivative bias that appears in real space. And then CS2 and CS4 are the parameters that correspond to 2 k-square counter terms that appear in redshift space distortions. And then this A2 corresponds to the alpha 2, the stochastic RSD k-square contribution. So A naught corresponds to alpha 1. So this notation is not very consistent with my lectures at the moment. And P shot corresponds to alpha naught. But and then B gamma 3, I think that at least for this one, I was consistent. So now you can see their best fit values. There you can see that they're all, some of them might appear a little bit big, but this is only because of some normalizations that sometimes I'm using, instead of k nonlinear, I'm using the cutoff, which is 1 megaparsec over h nonlinear scale, which is obviously too low, and this produces, which is obviously too high, and that's why the actual cutoff is like a small part of it. So when you divide by it, you get a big number. So these big numbers are only, kind of an artifact of the normalization. So if you were to normalize these things in terms of the actual physical quantities like k nonlinear and stuff, then you'll get reasonable numbers. So so for instance, this is true for all the stochastic parameters that I do normalize properly, and you can see that, for instance, the shot noise is about 0.3. You can see this alpha 2 is an order 1 number, etc. So all of these things, they make sense. You can check the reconstructed chi-square now by just computing simply delta P. So P best fit theory minus P data and convolving them with the inverse covariance. So you can check that your total chi-square is 107 for about 120 degrees of freedom. So this seems kind of, that the fit should be fine. And then you can plot data against the best fit model, and you can see that indeed these things, they work really well. And now basically you can go crazy. You can, go and analyze your BSM model, or you can try to study things like these projection effects related to the frequencies analysis, or you can try to include other statistics like the cross-correlation with symbolensing or the bispectrum, and the workflow will be exactly the same for these observables as well. So first of all, let me see if there are any questions. Okay. Okay, if there are no questions, then let me maybe discuss a little bit some aspects of this analysis, some, let's say, perturbations of the baseline analysis. So first of all, this notebook that I produced, basically you can see that it calculates all the plots that I was showing in my lectures, like IR summation, no IR summation. So you can always test with the data, for instance, to what extent IR summation is needed. So you see that if you don't implement IR summation, you'll have additional BO wiggles. So the typical thing that you're going to get is that you're going to get better, like more tight measurements of the Hubble constant, but also the chi-square will be bad. So that's why you can get an idea that really IR summation is important to get a reliable estimate of the Hubble constant from the data. Now, if you're using the projected galaxy observables, things like, for instance, the CL of galaxy-galaxy or the cross correlation between galaxies and CMB lensing, this will, like, CL of G kappa. So this will depend on the real space quantities. And the real space quantities you can also compute from class PT. So here I'm showing you result for the different correlations between galaxy and matter that are relevant for the projected observables. So these don't have any Russian space distortions because for the projected observables, you only have basically dependence on the perpendicular projection of the wave number on the perpendicular direction, so on the sky plane. So you can use the real space results. So it's nice because then you don't have to worry about fingers of God. It's also bad because then you get only, you get access to fewer modes. So there are some advantages and disadvantages. But you can extract all these different things relevant for the lensing observables from class PT as well, and then you can apply them, you can build a likelihood that compares these things with the data. So currently, in the likelihood that I was using, I'm only using the cross correlation between the both galaxies and the CMB lensing, and also CMB autopore spectrum that is in principle described by the matter-matter correlators, but the CMB lensing kernel has some extended high redshift, so basically even linear theory will give you a good job. So you don't need, strictly speaking, the EFT corrections, at least at the current precision for the experiments such as Planck. All right. We discussed this. Yeah, also we discussed a little bit the BOP. Can you see some distortions that you're going to get if you don't incorporate IR summation properly? All right. Now, there was a little bit of a discussion about the role of the covariance matrices. And I also mentioned that there are basically two ways to analyze the, to extract the power spectrum from the catalog. So you can use either the FKP estimator that Elizabeth introduced, and this estimator will return the power spectrum multiples convolved with the survey window function that describe the particular footprints on the sky. And then there is an alternative way based on the Wiener filter where you are trying to estimate the best way possible the unwindowed galaxy density field that then later gets imprinted onto the footprint and gets distorted. So you try to really estimate the unwindowed spectrum. This will return you the unwindowed estimator, the unwindowed P of K, which has the nice property that you can compare this with the data more easily. So basically this unwindowed power spectrum to first approximation, you don't need, you can compare it against your theoretical predictions right away, okay? So let's see now how these two different ways to estimate power spectrum compare. Are there any questions? Oh, okay. All right, so this is the data. Yes. Yeah, so this notebook right now, no. This notebook, Princeton Class PT is available. It shows the basic workflow, but it doesn't show the data. So this one I will upload on Class PT later, okay? Yeah, the other one is, yeah, I'll also upload the other one, the GGI tutorial. So yeah, this is available and all this, obviously all this GitHub web pages, you can go and check them out and see. I mean, they have all these things ready as well. Like for instance, here I was showing you some screenshot from Oliver's tutorial. So it's available, you can go through it. So you can see really how the density field of galaxies looks like. You can see what the mask is doing, shot noise. It has all the definition of the weights. And then, basically all the computations. Okay, so this stuff is publicly available. Please go and check this out. These two files are not publicly available yet, but I will make them public sometime soon. Okay. Any other questions? All right. So let's take a look at this data. The galaxy power spectrum. This particular power spectrum corresponds to the so-called high Z sample of BOSS, whose effective redshift is 0.61. Well, you can see here the monopole power spectrum, the quadrupole moment, and the hexadecapole moment. One striking observation you can make is that the error bars on the monopole are very tiny, and the error bars on the quadrupole and hexadecapole are much bigger. And this has to do with the fact that, well, basically, when you compute the covariance for different multiples, you remember I told you that, for instance, the quadrupole basically represents a cross correlation between the density field and the velocity field, which is very nice. But if you compute the covariance, you will have, again, the density field, density field, and velocity field. So you're going to get the density of the spectrum and the covariance again. And actually, there will be also some combinatorial factors that come from Legendre multiples that will work against you. That will, well, for instance, the covariance for the quadrupole will be factor of 5 bigger than the covariance for the monopole. So because of these different things, the error bars on the higher order multiples are big. And physically, ultimately, this is because of the fact that you're sensitive to these effects only along the line of sight, but along the line of sight, you have very few modes compared to the whole three-dimensional case, right? So that's why the errors grow. For instance, it would be really nice to have good measurements of the hexadecapole because it probes the velocity field, which is unbiased. But in practice, you always kill by the cosmic variance. The error bars on the hexadecapole are always large, so it doesn't play any significant role in the current data analysis. Okay, now we can also use n-body kit to get the estimate of the window power spectrum. Well, in this case, I'm actually using some data from one of the previous likelihoods that are discontinued now, that I also mentioned, some of the old BOSS likelihoods. You can, like, all this data is available. You can upload both the data and the covariance and then compare the measurements against the window 3 estimator. So the first striking feature that you will see is that the error bars in the windowed estimator are going to be much, much, much smaller. Okay. So does anyone have an idea why this is happening? So what is going on? So in principle, ideally, both methods should be estimating the same data, the same clustering signal. Why do you have much smaller error bars in this case? All right, so when we know that the errors are captured by the covariance matrix, right? But when we make these plots, what do we use to show the error bars? We cannot show the entire matrix, right? So what do we normally do? Yeah, we use the diagonals, exactly. So the diagonal elements are smaller here in the window case, but then in the window case, just by kind of definition of what the window function are doing, you should have more correlations between the modes, right? Because basically you start from the nice three-dimensional distribution, and then you project this onto the sky plane that will produce extra correlations. So the statement is that the, let's say, signal to noise is the same, but then you will have more significant off-diagonal elements that capture additional scatter. And this is something that you can easily check. Well, first of all, you can really, compare the two. You can see, yeah, look, this looks like a complete disaster. Look at these gigantic error bars. But again, it's all only a statement about the structure of the covariance. So yeah, if you take a look at so the nice part about the window 3 estimator is that the covariance, I'm going to show you in a second, the covariance is approximately diagonal. So actually this power spectra on the right, they represent the actual error bars much more closely, okay? Another, I guess, important observation is that you can see that the power estimated in both ways is different, right? The monopole is visually, visibly bigger in the case of the window free estimator, but this also because the window function has some normalization, and typically on large scales it changes the power, and so there is some sort of scale dependent way that the window function is affecting the power. That also makes sense because if you have a finite footprint on very small scales, you don't care about the shape of the footprint. But as you start hitting low k, so large scales, then you start getting sensitive to the exact form of the window function, and that's why, well, hence normalization. So that's why you will start seeing some departures from the window case, some different discrepancy between the windowed and non-windowed case on large scales. Okay, now let's take a look at the covariance. So here I'm just plotting the covariance for the monopole, quadrupole, hexadecapole in the windowed case and the window-free case. And you can see, well, so in this screen it's hard to see, but maybe you see that windowed already has like more, a more pronounced off-diagonal structure. And it's even more obvious if you only plot like a tiny part of the covariance matrix. So basically, you can see that in the window case, you have beans right next to the diagonal that are super correlated, so that have very high degree of correlation. Here in this color scheme would be green, so like they're correlated by almost like 70% or so. And then even if you go far away from the diagonal, still you get something like 50% correlation, right? So this is the kind of main drawback of the usual windowed estimator, that you're extremely sensitive to what the covariance is doing, right? At least the structure of the covariance becomes, the covariance becomes very, very, very off diagonal. However, for the window-free case, you can see that, obviously you have some relatively strong correlation for the bin just next to the one you're looking at, but then the correlation otherwise quickly dies off. Yes. Yeah, I must say I don't really know the answer to this question, but I'm sure that if we just write down the estimator, we should be able to see how this comes about. Okay, so I don't think that there is a simple answer to this question. Okay, very good. So now we can also see, okay, we also see some kind of noise in both cases, right? That the diagonal elements kind of, the power in the off-diagonal elements fluctuates. And a significant part of these fluctuations is actually the numerical noise. So in this case, we're estimating the covariance matrix using the empirical estimator from the mock catalogs produced by the survey. So we have only 2,000 catalogs, which seems like a lot, but in reality is not enough kind of to suppress this noise significantly. And even for BOSS, there were some sigma-ish or half a sigma systematic shifts of the cosmological parameters produced by the noise in the covariance matrix. So this is also another important fact to keep in mind if you're using the covariance matrix from the empirical estimator. However, some of these problems can be alleviated if you're using the analytical covariance matrix. So there was a great paper by Jay Wadekar and Roman Skachimara where they developed the analytic covariance matrix model for BOSS that includes all the effects that Elizabeth mentioned, the supersample covariance, the trispectrum, and things like that. And here you can see the results. The windowed analytic covariance matrix looks just like a very nice, very smooth version of the sample covariance. So leading order kind of, captures well the diagonal, and the structure of the correlation with the neighboring beans is also captured quite well, but then it doesn't have noise in the off-diagonal elements. So this is always the kind of advantage of the analytic covariance, that in general, it completely kills the sensitivity to the sampling noise that otherwise could be a significant effect, even if you have built your empirical covariance out of thousands of mocks, okay? So this is something to keep in mind. Well, another effect that I would like to mention here in relationship with the structure of the covariance matrix is that, well, as you can see, because of, this covariance has very significant correlations, right? So that means that different k-beans are correlated. So when you impose a k-max, right? So when you impose k-max, let's say 0.2, as everyone does, you still keep the sensitivity to other k's through the covariance, right? So in other words, your, let's say, response of your window power spectrum to the actual underlying dark matter power spectrum has some finite width. So you cannot say that 0.2 HR megaparsec in the galaxy power spectrum maps directly onto 0.2 HR megaparsec in the matter power spectrum anymore. It has some finite spread, the response function. And this response function otherwise is greatly reduced if you're using the window-free estimator, because the covariance matrix is more diagonal. So you can clearly tell that, yeah, if you cut at kmax 0.2, then this corresponds to a cut at kmax 0.2 in the idealized three-dimensional case. So this is another property to keep in mind, that there is some mode leakage introduced by the covariance matrix. Okay, and then, yeah, and then there is this data analysis part that we've already discussed. So I think that I mentioned, well, I went through all the important things that I wanted to discuss. It's almost 1 hour. Okay, so maybe I can ask you if you have any questions about any of the part of this workflow. Yeah. Mhm. Yeah, okay. Very, very roughly, so it's based on this Wigner filter. Right, so basically, okay, the idea is that what you see in a galaxy survey is always the density field convolved with the window function, right? I think this is fine. So you have the measurements, delta galaxy data, right? So in theory, this corresponds to a window function that in principle involves, both summation over different k's and l's, window function times, well, the data vector, let's say delta g true, right? The true galaxy density field. So the usual FKP estimator basically just computes the power spectrum of this quantity. Now, what the window-free estimator does is that you're considering this. So you say that, yeah, sure, imagine I have some data. This is fine. And now I want to build a likelihood for it and minimize this and try to extract the best estimate for the true unwindow galaxy density field. So obviously, to evaluate these things, you need some sort of simulations to do that, right? Because in principle, if you only have one realization, you can't do anything. But if you have enough simulations, you know what the window function is, then you can undo this and you can get an estimate for the delta galaxy true. So this is in principle what this is doing. So in other words, if you want a practical comparison between the usual FKP estimator and this, is FKP is super easy. You run Embody Kit, 1 second, it's done, or maybe 1 minute, you have all the measurements. Now for this, you need a little bit of a build up, right? You need to produce some, you need some mocks, and then you need to run some sort of minimization algorithm that will estimate this. But once this is done, that's it. So you need to do it only once. So it takes maybe a couple of hours, but once you get this, the unwindow galaxy density field, now you can compute everything, and then it will not have any window functions. And this approach is especially nice, for instance, if you want to work with the bispectrum, because the window function for the power spectrum can be estimated more or less easily, but for the bispectrum is a gigantic pain. However, with this kind of estimators, you can extract it. Okay. Yes. Yeah, this is an excellent question. So typically, yeah, within the collaboration, there is some group that runs the mocks. But running the mocks is always challenging. Well, first of all, because you have to use some sort of, you cannot run the full on-body simulation, that is too expensive. So you have to use some sort of approximate solver like Cola, or, the DESI are using the mocks based on the Zildovich approximation. Then you have to assume cosmology for running those. You have to assume some sort of prescription how to go from dark matter to galaxies, typically using some sort of HUD prescription, which is fast to implement. This is fine, but it's very easy to produce a mismatch. It's very easy to produce the mocks that have properties that do not exactly match the properties of your galaxies. This, by the way, what happened to DESI, and if you've seen the papers, they introduced additional weights, additional corrections to account for the mismatch between the mocks and the data. So in general, it's a very difficult problem. In general, I think you should not trust the sample covariance matrices because, well, one of the reasons is precisely that, because they were produced assuming some like meta parameters that were calibrated and maybe that are not going to match the actual measurements. So yeah, it's a hard task. So that's why doing this analytical covariance matrices is, a very nice way to kind of get out, to get around this issue. And in principle, estimating the covariance is not so hard. In an approximate way, right? You can always generate some sort of linear Gaussian fields, put them on the sky plane. You can estimate the window function this way, and you can run this kind of algorithm to compute these things. So I would say that, in this, once you decided to go in this path of using approximate methods, at some point you realize maybe you don't need to use simulations at all. You can just produce linear fields or Zeldovich fields, just maps without any evolution, without running on body, and then for the estimation of the covariance matrix, they will be as good as running approximate simulations. I think that, for instance, for DESI, for the likelihood that I mentioned, for DESI, this is what we're doing. We're producing, we're just drawing kind of, putting Gaussian fields on a sky plane, and then you can implement all the survey effects easily, but at the level of the Gaussian fields. Of course, it's going to miss some of the important contributions, like the supersample covariance due to mode coupling. It's going to miss the trispectrum. Okay, that's the price that you pay. Either that, or you pay this price of the uncertainty somewhere else. Okay. Yeah. I mean, we know in practice, based on the work done on the periodic box simulations, we know that many of these things, like a supersample covariance or the trispectrum, at least for the range of scales we're looking at, they don't matter as much. So maybe you're going to make, let's say, like a 10% error on the error, which doesn't matter, right? I mean, we're talking about like one sigma effect. One sigma is like 100%, right? 10% error of an error is not a big deal. So at the moment, we have this, estimates that are analytic. We have empirical validation that in general, these things, at least for the range of scales we're looking at, these things are not very important. But in general, look, covariance matrices, as you learned from Elizabeth's talk, is a big field which is open. There are many challenges. There are big groups, development methods. So altogether, it's a very active field, and things are far from being settled there. Okay. Any other questions? Hmm.